All right, IBAASL2. We have basically just been doing a lot of application practice because you guys are getting ready for that second opportunity on applications after the break. I'm going to do two more problems with you today. One problem is going to work out very nicely and can be done just with algebra, no calculator necessary. And then the other one, I'm going to show you how the algebra gets a little too insane and we actually have to resort to a calculator. And I'll talk more about how that's going to look in a testing situation. But right now, let's just focus on the math. First problem, we have a parabola, an upside down parabola, and then underneath that parabola is a rectangle that's inscribed. So this rectangle goes up and touches 2 points on the parabola, and it's bound by the x-axis, and then touches the parabola at those 2 points. We're going to find the dimensions of this rectangle so that we will maximize the area of the rectangle is what I meant to say. Find the dimensions of the rectangle that will maximize its area. Yeah, you guys get it. Area of the rectangle. So this curve is 9 minus x squared. That's the equation of it because they give it to us right here. So I'm going to call this distance right here, from here all the way over, we're going to call this x. Now, if you go x over to the right and then plug in that value into the function, that means that this distance up is the y value of the function when you input x into the function. So this side right here is 9 minus x squared. That's the first hurdle you got to get over with these like inscribed problems is like if you put in an x value to the function, then up on the y-axis, that will be 9 minus x squared. It's whatever input you put into the function, and that's the output is 9 minus x squared. Excuse me. So the dimensions of the rectangle, we're going to write an equation for the dimensions of the rectangle. I've only written part of the side here, but we need the full side. So there's another x over here, which means this entire side is going to be 2x. So area of the rectangle is going to be 2x times 9 minus x squared. That's length times width. I'm going to clean that up or distribute a little bit rather than use a product rule. I guess we could use a product rule to find the derivative, but I'm just going to distribute that 2x. So we get 18x minus 2x to the third. Now that is the area equation. If we want to figure out when that equation is at a maximum, we can use derivatives. So take the derivative of the function, we get 18 minus 6x squared. Now that's the derivative, but we want to figure out when that's at a maximum, which means that we need to figure out the turning point, the local max, local min, whatever, and set it equal to 0. Subtract 18 from both sides. Divide by -6. We get 3 is equal to x squared. Then take the square root of that, and we get plus or minus the square root of 3 is equal to x. Now, because x was just a distance to the right, I can actually toss out the negative and say that the square root of 3 is the x value. Now, in order to make sure that's actually a maximum that I've found, I should probably check the second derivative. So we'll check second derivative with another color. So a double prime of x is equal to just negative 12x. And then if I plug in a root 3, that will be negative, which means negative is concave down, which means it is a relative maximum. Just making sure I didn't find a minimum or something like that. Now, back to what the question asks. It says, find the dimensions of the rectangle that will maximize area. Well, remember that we just found x, which is just this side right here, and it was root 3. So if this side is root 3 and this side is root 3, that means that one of the sides is 2 root 3, but then the other side is going to be 9 minus root 3 squared, which root 3 squared is just 3, and you get 9 take away 3, which is 6. So, final answer, two root 3 by 6. That's it for that one. The classic two-post problem with a wire strung in between them. There's a 10-foot pole and a 25-foot post. 10-foot and 25-foot posts are 30 feet apart. A wire runs from the top of one post to a point on the ground in between the posts and then to the top of the other post. Where should the point be on the ground in order to use a minimum of wire? The first thing we got to do is draw a picture of this situation. So here's my ground. We're assuming that these posts are perpendicular to the ground and not slanted, which means this is a right angle. Here's a 10-foot post, and the other one is a 25-foot post. And then there's some point on the ground where you run a wire down to the ground and then over to the other top of the other post. And the whole thing, the entire thing is 30 feet apart. So if I kind of zoom in on my picture here and add some more things, let's call this distance right from here to here, let's call this x. And then the distance on the other side is going to be 30 take away x, because they both have to add up to 30. If one of them's x, the other one is 30 minus x. Now using a little bit of good old Pythagorean Theorem, which is a squared plus b squared equals c squared, which means this side squared plus this side squared equals this side squared. If you do x squared plus 10 squared equals that side squared, you can square root the hypotenuse to figure out what that side is. The hypotenuse is, So this side is 100 plus x squared. It's the square root of 100 plus x squared. Same thing can be done for this side using Pythagorean Theorem. You square the two legs and then square root them, add them together and square root them. So this side is 30 take away x squared plus 25 squared. So now our length of the wire, let's just use what do you guys want to do? W of x for wire? It's up to us. That is the square root of 100 plus x squared, and then add the square root of 30 minus x squared plus 25 squared. So if we want to figure out when the wire is at a minimum, we are going to need to take the derivative of that function. So w prime of x. This first one here is I don't like that. It's a chain rule, you guys, because there's a function inside of a function. So you take the derivative of the outside with the inside the same, bring the 1/2 out in front, and you get 100 plus x squared, but then you have to do times, you have to drop the power by 1/2, and then multiply times the derivative of the inside. Then it's another chain rule in the back, so you get 1/2, oops, I forgot a little parentheses in here, times the derivative of the inside unchanged, which is 30 minus x quantity squared, I almost did it again, plus 25 squared, all to the negative 1/2, and then times the derivative of the inside, which the derivative of the inside is basically just another little chain rule. It's a chain rule for this guy right here, because it's a function inside of a function. So it's the derivative of the inside with the outside unchanged, derivative of the outside with the inside unchanged. So that's 2 times 30 minus x. Drop the power down 1, and then you have to multiply it times the derivative of the inside. And then I believe we're good. Now let's play some cleanup. Let's turn things into square roots. Let's move negative powers to the denominator. So this whole first fraction here is 2x in the top, and then in the bottom we get 2 times the square root of 100 plus x squared. Now this whole second thing here, let's do the same thing where we move negative exponents to the denominator, see if there's anything that cancels out. So this is plus big old fraction. Up top it'll be negative 2 30 minus x, and then all over 2 times the square root of 30 minus x squared. I'm going to change that 25 squared into 625. Yeah, I think we can do a little more cleanup because these 2's cancel out, and we can distribute right here. So w prime of x, just to remind myself what I'm doing here, this is x over the square root of 100 plus x squared, and then add these 2's cancel out, and then the negative distributes, so we get 30 minus x. Sorry, no, the negative should distribute there. And so we'll get negative 30 plus x, which is the same thing as x minus 30. And then that's all over a big square root of 30 minus x squared, quantity squared, plus 625. Now, that's the derivative as cleaned up as we're going to get it, I think. We could do some common denominator work, but man, it's going to get ugly. Now, if you set this thing to 0 and you try to solve, I've been down this road, and you can try. You can like move one fraction to the other side. You can do a little cross multiplication, and then there's all these square roots. So you like want to get rid of the square roots by squaring both sides, but then you end up with like really large polynomials, like things to the 4th power and 5th power and stuff like that. So this is a situation where if you end up with like trying to figure out how to solve something to the 5th power or something like that, and you don't know how to factor it, this is probably a situation where the algebra got too insane and we need to use a calculator. So what I'm going to do is punch this into y1 in my calculator. So let's see. Get rid of that. X divided by the square root of 100 plus x squared. Then it's going to be, what, x minus 30 up on the top. Sorry, I'm just fixing my equation a little bit. And then in the bottom, we have the square root of 30 minus x squared plus 625. Now, if you punch that all in, be careful to use a lot of parentheses. Now, if you use parentheses properly and you hit graph, you're probably going to see a screen, like, because your graph is doing whatever screen you had last on there, and you might not see an answer. The hardest part about this method is finding a correct window. So I played around with my window a lot, and I finally got something that looks decent where I can see where it crosses the x-axis. We're trying to figure out where it crosses the x-axis because I want to know when this is equal to 0. And that function is equal to 0 when it crosses the x-axis. So my window goes from negative 10 to positive 25, and then like negative 2 to positive 2. And I can see a nice spot where it crosses the x-axis. Then you're going to want to hit second, and then trace, which is essentially the calc menu. In that, you're going to look for the thing that says 0. Now 0 works the same way that minimum and maximum do, where you have to tell it a left and a right bound. So here, I'm going to hit 0 on my calculator, and then it's going to say left bound and right bound. And then a right bound. And then you're going to give it a guess. So put your left bound somewhere to the left of the where it crosses the x-axis. Put your right bound somewhere on the right, and then move your guess somewhere close, and then hit enter again. When I do this, I get x is about 8.57. Which, back to my original problem here, that means it should be 8.57 feet from the 10-foot post. So my final answer oh gosh, I said left post. I meant, because we don't know which one's on the left and which one's on the right, from the bottom of 10-foot post. So, still an optimization problem, still using derivatives, but the algebra got too crazy, so we had to resort to a graphing calculator. All right, you guys, I uploaded a review or an applications practice worksheet for you guys to do over the break. Be safe out there. Have fun.